Welcome to the Explainer. So have you ever given a seemingly brilliant AI a really complex problem, only to watch it just spectacularly faceplant on the specific details? Yeah, it's a totally universal frustration. Large language models, for all their massive computational power, they have this baffling tendency to get completely lost in the weeds right when we need them to be their absolute sharpest.
So why exactly do smart AIs make such dumb mistakes? Well, often when a model fails at a complex task, it's because it literally plunges headfirst into the specifics of a prompt. I mean, think about how you or I would solve a tough physics or engineering problem. You don't just start mashing numbers together on a calculator, right? You figure out what kind of problem it is first. But AI, by default, often skips that crucial step. It tries to solve everything all at once, in a straight line. And in doing so, it makes these tiny intermediate logic errors along the way that just snowball into a completely wrong answer. It literally misses the forest for the trees.
But actually, there is a brilliantly effective fix for this. Back in October of 2023, the folks over at Google DeepMind published research on a real game-changer of a technique called step-back prompting. Basically, this is all about evoking reasoning via abstraction in large language models before tackling the specific details. This technique is absolutely the hero of our story today. It essentially forces the AI to zoom out, identify the core principles at play, and find that forest before it starts chopping down trees. To get you mastering this technique, here's our roadmap for today. 1. The AI reasoning problem. 2. Enter step-back prompting. 3. The two-step method. 4. Step back versus other methods. And finally, 5. The performance results. Let's dive in.
Section 1. The AI reasoning problem. Missing the forest for the trees.
Moving right along to Section 2. Enter step-back prompting, the power of abstraction.
Okay, let's dive right into this. By prompting the model to derive high-level concepts and first principles first, we build a rock-solid foundation. This intentional pause for abstraction, that is the magic ingredient that prevents those frustrating cascading intermediate errors. You are effectively telling the AI, hey, ground yourself in reality before you try to do the math. So there are two fundamental mechanics to this technique. Step 1 is abstraction. You prompt the AI to focus on a higher-level concept or principle related to your question. Then, Step 2 is reasoning. Once the model has retrieved that high-level abstraction, you prompt it to use that concept to reason through the specific details of your original question. It's a highly effective 1-2 punch.
Section 3. The two-step method. In action with the ideal gas law.
Now, theory is great and all, but to really understand how this changes your prompt engineering, we need to look at a concrete, complex problem. Here is the exact initial question. What happens to the pressure of an ideal gas when temperature increases by a factor of 2 and volume increases by a factor of 8? If you just feed this to a baseline model, the competing variables, temperature going up while volume also goes up, they often completely confuse its linear processing. It tries to calculate the pressure changes simultaneously and just gets totally tangled up in the numbers.
So what do? We don't ask that question directly. Instead, we manually intervene with our first step, the step-back question. We ask, what are the fundamental concepts or principles involved in this problem? Notice how we aren't actually asking for the final answer yet. We are forcing the AI to hit pause and basically fetch the right tool from its cognitive toolkit before it starts hammering away.
And look at how the AI responds to that abstraction prompt. It outputs exactly what we need. It gives us the ideal gas law, PV equals ZRT, and then correctly defines all the variables. It successfully retrieves the exact foundational formula it needs. It isn't distracted by the factors of 2 or 8 yet. It just knows the fundamental rule of the universe it's going to have to apply.
Okay, now we move to the reasoning step. We prompt the model to use that specific formula to answer our original question. And this brilliantly illustrates the sheer power of the technique. The AI substitutes the values, P times 8V equals NR times 2T. Then it mathematically divides both sides by 8V to isolate P. Because it has the formula clearly laid out as its anchor, the algebra becomes a super simple logical operation for the AI.
And boom, it effortlessly arrives at the satisfying conclusion. The pressure decreases by a factor of 4. By breaking the prompt into abstraction first and reasoning second, we guided the AI to flawless execution. We entirely removed the cognitive overload that typically causes hallucination or logic failures in those really complex tasks.
Section 4. Step back versus other methods, why it's different.
Now, if you're a seasoned prompt engineer, you might be wondering, how does this actually differ from what I'm already doing?
Well, let's compare it first to the widely used chain of thought prompting. Chain of thought forces the model to solve a problem step by step in a strict linear sequence. And while that's helpful, it's rigid. If the AI makes one faulty assumption in step 2, that error compounds all the way down to step 10. Step back prompting, on the other hand, is much more expansive. It abstracts high-level concepts first, locking in the foundational logic from the very start, which drastically reduces the chance of those early, detail-oriented errors compounding.
We can also briefly distinguish it from take a deep breath prompting or decomposition. Take a deep breath just asks the model to slow down, but it still functions linearly. Decomposition breaks a big problem into smaller subproblems. But step back is different. It doesn't just chop a problem into pieces, it rephrases the original question into a more general concept. Abstracting and generalizing the problem is the true differentiator here.
Section 5. The performance results. Hard data on Palm 2L. So, does this abstraction step actually move the needle in the real world? Well, Google DeepMind ran the numbers across some intensely difficult, reasoning-heavy tasks, and the metrics they discovered are actually quite dramatic. Now, what's really interesting about these numbers is the sheer scale of the improvement on the Palm 2L model. In TimeQA, which is a complex temporal reasoning benchmark, step-back prompting yielded a massive 27% gain over the baseline. For MMLU chemistry, an 11% boost. We see a 7% jump in both physics and the musique benchmark, and a 3.6% gain in strategy QA. Guys, these aren't rounding errors. These are substantial, real-world leaps in cognitive capability just from changing how we frame the initial prompt.
So the crucial point is this. What should you actually take away from this explainer for your own daily workflows? First, expect substantial performance gains, anywhere from 7% to 27% on complex reasoning tasks. Second, use this method as a direct shield against error by forcing abstraction. And finally, remember that this is highly robust and model agnostic. While it was tested heavily on Palm 2L, research shows this works beautifully on GPT-4 and Llama 2 70B as well. It's truly a universal upgrade to your AI toolkit.
All of this leads me to a final thought I want to leave you with today. We build these vast, incomprehensibly complex neural networks capable of processing millions of data points a second. Yet, if an AI requires us, the human operator, to manually force it to zoom out and understand the bigger picture before it can do basic physics, what does that reveal about the true nature of machine reasoning? Is it truly reasoning at all, or is it just highly advanced pattern matching, sitting there waiting for us to give it the right blueprint? Thanks for joining me on this explainer, and as always, keep questioning.